In all fiber optic systems, it is necessary to join two fibers together with low signal losses and reflections. Fiber optic connectors provide non-permanent fiber interfaces to other fibers, network transceiver equipment, and cable management products such as patch panels. The ideal optical connector holds the fibers in perfect alignment in 3 axes. This alignment must be maintained over hundreds or even thousands of connect-disconnect cycles to provide stable, repeatable attenuation characteristics. The most important element of the connector plug is the ferrule, which provides the precise alignment and centering of the optical fiber. Ferrules can be made of ceramic, metal, glass, or plastic. Zirconia ceramic ferrules or ceramic ferrules with metal inserts are most widely used, providing the best tolerances and durability. The body of the plug holds the ferrule, the coupling mechanism, and the boot. The body contains either a threaded push-pull or bayonet coupling mechanism that mates the plug with the mating receptacle and also provides a keying function that allows the connector to mate in only one position. Strain relief of the cable is usually by a crimp sleeve, which firmly secures the aramid yarn in the cable to the plug body. Strain relief can also be provided by adhesives that permanently bond the cable buffer materials to the plug body. At the end of the plug body is the boot, which functions as a bend radius limiter for the cable entering the plug body. Another critical component is the mating adapter and its internal sleeve that aligns the two mating ferrules. Like the ferrule, sleeves are most often made from ceramic and can be either a split or solid construction. The alignment sleeve must precisely align the two precision ferrules by means of the ferrule's outside diameters. This alignment must be done while providing a low friction fit over a wide temperature range. Over the years, fiber tolerances have greatly improved, along with the mechanical tolerances of precision parts of the connectors. Early connectors suffered from poor alignment tolerances and mechanical stability problems due to loose fiber tolerances and mechanical tolerances of the connector design. However, they were installed by the millions. With new connector designs, the body and mating adapter provides a keying function, allowing the connector to mate in only one rotational position. This, combined with the tight tolerances of today's optical fiber, ensures compliance with the Telcordia GR3 26 generic requirements repeatability standard of less than 0.2 dB connection loss for single-mode fibers. In an attempt to reduce the negative effects of poor mechanical tolerances, some early connectors incorporated lenses. Lensed connectors work by expanding the beam exiting one fiber and using a second lens to collect that light and refocusing it on the core of the second fiber. The main advantage of this approach is that the connector is less sensitive to alignment tolerances, so attenuation will remain more constant in the presence of vibration or temperature cycling. Disadvantages include greater complexity, higher cost, and the fact that the lenses and resulting air gap between fibers result in higher attenuation. The earliest design by the Deutsch company in the 1970s used a wet lens approach and was a field terminable connector. Later lens connectors included Radial's Optiball connector used on OTDRs, the Lamdeck expanded beam connector made by Eastman Kodak, and a series of expanded beam multi-fiber connectors developed by Tyco for harsh environments such as military and aerospace applications. As the fiber optic industry evolved, numerous standards were developed. The role of standards is to make sure that mechanical and optical considerations are specified for the benefit of all. A key standard is the Fiber Optic Intermatability Standard, or FOCUS document. Known officially as the TIA-EIA 604, the standard covers various connector styles, their configuration options including keys, fiber counts, polishes, mounting options, descriptions, and tolerances. The written objective is the minimum physical attributes of mating connector components so that any combination of plugs and adapters will mechanically intermate and when mated will meet a common level of performance. Even though there have been vast improvements in mechanical tolerances of modern fiber and connector products, most connectors still have higher optical losses than splices. The ITU G.671 standard specifies a maximum attenuation of 0.5 dB per mated pair, while the Telcordia GR326 standard specifies a 0.4 dB maximum. Both standards are focused on single-mode connectors where the fiber itself has attenuation levels of 0.3 dB per kilometer. For premises and other multimode applications, the TIA-EIA 568 standard specifies a mated connection of 0.75 dB maximum. Within connectors, fiber separation and misalignments are the chief causes of signal attenuation, but poor quality fiber, differing fiber types, and the quality of the fiber end face also contribute to total connector losses. In addition, stresses placed on the fiber such as overcrimping or macro bending at connector boots can add attenuation. Another major attribute of a fiber optic connection is its reflectance. Reflectance, also measured in decibels, is the percentage of light reflected from the glass-to-glass surface contact of the mated connection. This reflection can disrupt the operation of laser light sources used in transmitters, especially in DFB lasers. This affects the quality of the signal and can result in unacceptable bit error rates, noise in analog systems, and latency of data communication systems. Fresnel reflections can be minimized in a connector plug by polishing the fiber end faces to specific profiles. These include a domed profile known as a physical contact or PC finish, and the ultra-physical contact or UPC finish. Another profile, called the angled physical contact or APC finish, slightly angles each of the mated fiber ends to 8 degrees. The UPC polish is used most often in high-speed digital systems, while the APC polish is used in analog, dense wavelength division multiplexing systems, with optical amplifiers, and in fiber-to-the-home installations. PC connectors have a reflection value of -40 dB, which means that the connector reflects 1/100th of 1% of the incident light back towards the transmitter. An Ultra PC polish has only 1/10th of that level and are rated at -50 dB or better due to their improved spherical profiles. Producing PC polishes is a precision process. Even a slight deviation from the correct spherical or angled profile renders the connector unacceptable. This makes PC connectors more expensive than conventional types. For this reason, these polishes are made using automated polishing equipment and are 100% visually inspected, followed by optical loss and reflection testing. Multimode systems are usually much more forgiving of reflections. This is due to the fact they use light-emitting diodes or vertical cavity surface-emitting lasers, or VCSELs. Both LEDs and VCSELs are insensitive to Fresnel reflections, so hand polishing to a flat finish is adequate. A problem with this approach is now appearing. Because single-mode systems are sometimes being installed in premises applications, many technicians and designers do not understand the effect of reflections because they are accustomed to installing and then measuring end-to-end attenuation levels and not reflection levels in system tests. Because the core and mode field diameter in single-mode fibers is much smaller than in multimode fibers, tolerances for single-mode fiber as well as their connectors must be much tighter. This makes field installation of connectors much more challenging. Historically, for this reason, single-mode terminations are mostly factory terminated on short lengths of 900 micron buffered fibers or 3 mm cordage known as pigtails. The pigtails are then spliced onto the ends of the optical fibers. Connectors have evolved with the communications industry. Today's users have a multitude of connectivity needs, and the fiber industry has responded with innovative solutions. These include backplane connectors, high fiber count connectors for use with ribbonized fibers, small form factor connectors used on high-density optical transmission products, and also for applications including fiber to the home and dense wavelength division multiplexing where space is at a premium. In the following chapters, we'll take a closer look at the different connector types and how they are implemented in modern fiber optic networks.